video, we are going to look into the mathematics of general relativity. We are going to build up the basics of the foundation of the mathematics step by step, one by one, so that we can understand all the components, the detailed structures, the space-time curvature, tensors, everything related to general relativity. I am keeping this video to be as simple as possible, and I will make the formulations of mathematics pretty simple using analogies which are very easy to understand, so that we can get to the basic root and understand the concepts of relativity using the mathematics involved in it. My name is Shaunak, and you are watching this video on my channel Physics for Students. Season's greetings and a warm welcome to watch this video. So before we go ahead and start watching this details of the video, let us look into what are the topics that we are covering. So yes, we are covering Euclidean geometry, then we will move to Euclidean metric, covering Newton's law, what is gravitation, gravitational field, how gravitational field and Christoffel symbols are related to each other, then understanding a very important concept which is called a connection. What is the geometric meaning of Christoffel symbols, and Christoffel symbols, how are they written in terms of the metric, and finally we will summarize what we have learned. So first we start with the Greek philosopher and geometer Euclid. Euclid was an ancient Greek mathematician, active as a geometer and logician. Considered to be the father of geometry, he is chiefly known for the Elements treatise, which established the foundation of geometry that largely dominated the field until early 19th century. So here are a few of the key results of Euclidean geometry. The internal angles of a triangle add up to 180 degrees. Two straight lines that are initially parallel can be extended, which is known as Euclid's fifth postulate or the parallel postulate. The area of the circle is given by pi r squared, and the Pythagoras' theorem, which is the length of the hypotenuse squared equal to b square plus perpendicular square. This is something elementary which we learnt in the schools, but as you understand, mathematics is always built by adding one concept on the other, so it is good to look into that. Okay, so we move on to the next part where we can define a space where Euclidean geometry works, which is known as Euclidean space. Now it can be two-dimensional, for example this tabletop, or it can be a three-dimensional, for example a cube. Now working on the approximation to the ordinary space that we look at. So this may be a statement of the obvious, but we will see that Euclidean space is just not one of many possible spaces. Curved surfaces, for example, are not Euclidean. On the surface of a sphere, for example, lines of longitude start off parallel onto the equator but meet at the poles. Now in relativity, we deal with two types of four-dimensional Euclidean space. The first is the flat space-time of special relativity, where Euclid's parallel postulate holds, and the curved space-time of general relativity. So returning to Euclidean space, Pythagoras' theorem can also be used in three-dimensional dimensions to calculate the corner of the opposite length of a rectangular cuboid. So what we do is that we will use this cuboid ABC, and we just define this length as 1, 1 and 2. I will just keep it simple just to give you the basic idea so that you can understand. So here we take the 2 square plus 1 square plus the height, width and breadth, and from there we calculate square root of 6, which eventually results into 2.45. Okay, so now why I showed you this, because if we take the same cuboid from here and we try to use this same thing, so we get L squared equal to A squared plus B squared plus C squared. So what happens is that using the Cartesian coordinates in 3 dimension, which is as written, the distance or the distance between 2 points x, y, y1, z1, x2, y2, z2 can be given as this, right? Or what I can do is that alternatively in terms of the interval, I can write it as delta L squared equal to delta x squared plus delta y squared plus delta z squared. Now why I'm showing you this delta, you will soon understand, because this is the first notion. We are trying to use the Euclidean geometry in three-dimensional space, and this is known as to be the space has to be Euclidean, I mean to say, in order to make it true, and this applies for any interval when it is working for Euclidean space, right? And this is what we arrive to the first fundamental important mathematical concept, which is called the metric. So I mean to say the metric is basically a function defines distance between 2 points. However, this interval actually applies when it is working, remember, in Euclidean space. Okay, so we now move to the second part of our video, where we will be working a little bit on the Euclidean metric, which is equally important for us to learn. Now, as I told you, the metric is a function that defines the distance between 2 points in a particular space. Once we know the metric of a space, obviously, theoretically at least, we can know everything about the geometry of that space, what is the metric, or its fundamental importance. So because of the nature of the Euclidean space, the distance function is constant. It doesn't matter where it changes. So this one, if you say that this is constant due to the nature of the space, that means that we can plug in any values of x1, x2 minus x1, y2 minus 1, and so on, and end up with the correct answer, right? And the distance between points x1, x2, y2, and z2. So now this is something which is not same for other spaces, right? This is not same for other spaces, but the distance function is, I mean to say, is not constant. So to get over this problem, we now introduce a kind of a new notion, which is this one: dlx, dly, dlx, dx, and dy. And what we call these dlx, dl, dxy, dyz, all those, I mean to say, for 4-dimension, etc. This would be what it's called coordinate differentials. Although we discard dl, it is dx, dy, and z. So these are called coordinate differentials. And when we used to describe the distance between two infinitesimal closed points in space, we call this distance as line element. I mean to say, this is between, when it is two infinitesimal closed point, it is called line element. So the Euclidean line element in Cartesian coordinates, this is the, so this is represented as this one, right? And let me go back to that. Yeah. So this is the Euclidean line element, which is represented in Cartesian coordinates, where we are taking dl equals to, that is the length, equals to dx square plus dy square plus dz square, which is exactly the same as L square is equal to x2 minus x1, and so on, which is the same in the Cartesian coordinates, but in case of a curved space, we need to understand something in a differential way, so we are using those. Okay, so now let us see that if this dl is equal to dx squared plus dy squared. So what happens is that you see this 1 into dx squared term and 1 into dy squared term and 1 into dz squares come. These are actually the matrix coefficients, right? So we can arrange them. So these are 1, this one, this one. These are basically coefficients. So dx multiplied by this one equals to 1, and so on, right? So that is how it is. So we can, and all other products remains the same. So we can arrange them, and it looks like a nice kind of a matrix like this, right? So this matrix actually tells us how to multiply the differentials dx, dy, dz, and we can see this in this kind of a matrix, right? Now seeing that dx into dx times dx equals to 1, and dy times dy equals to 1, and dz times dz equals to 1, all other products of dx, dy, and dz equals to 0. So the indices, if you identify I, j, and g by reference of rows and columns, so this is the one which comes when we write. Now note that here is a bracket, which means that we are referring specifically to the entire matrix and not to individual components. So this is just a convention, right? So here it goes g1 equals to 1, 1, g22 equals to 1, and g13 equals to 0, and so on. Okay. So this is something important. When we are representing this into Euclidean matrix, we multiply these coefficients with 1 in order to make it in a nice 3 by 3 matrix where all other products goes to 0, and this bracket denotes that we are specifically denoting the entire matrix but not to individual component. Okay. So now we see that this metric actually helps us to form the metric tensor of general theory of relativity, and this is something which is called a symmetric tensor. So G mu nu equals to G nu mu, and yeah, so the metric tensor in relativity is symmetric tensor and bilinear in form. This mu nu actually denotes 4 dimensions of space-time, and you will also see there are certain duplicate terms, so 0 1 equals to 1 0 and so on. So this actually reduces from 16 components to 10 components. I have shown this pretty clearly in one of my earliest videos on general relativity called Ricci tensor, Ricci scalar and metric tensor, which is there in the playlist of my general relativity video. If you want, you can look into it. So this is just a kind of a quick note that how the 16 components of the metric tensor reduces to 10 components because of the duplicacy, and how this G00 etc. comes. We have just seen these are the coefficients. Once they are multiplied in from and forms a line element, it can be arranged in a matrix, right? So till now we have understood what is the metric, how it starts with Euclidean geometry, but now we turn to the real physics and we wait for someone whose birthday is nearing very soon, that is Sir Isaac Newton. And physics, as we know, is not complete by Newton's law of motion. So just a quick glimpse, I mean to say, let us not go into that. This is again, you might say it's a repetition. So, and the first law tells that an object will remain at rest until acted upon by external force. This is a quick kind of a, visual treat that this person is kicking the ball unless acted upon by extra force, so it would stray. And we know that inertia is the property of a body to resist, and that is called the law of inertia. And the mass of a body is a measure of its inertia and is called the inertial mass. So we straight away move to the most important, that is the second law of Newton, which states that if a net force acts on an object, it will cause an acceleration of that object, and the relationship between an object's mass m and its acceleration a is given by this famous formula F equals to ma. Note that F and a I have written it in bold because I want to make sure that it is a vector notation, and it also can be written in scalar notation, right? So the first vector form of this law is also states that the force equals the rate of change of momentum, which I have shown P equals to m of v, where momentum equals the mass of the object times its velocity. Now another way of stating the same law is this one, like P equals to differential of P and T, where I take this one further, right? So we can, as you can understand, it's pretty simple. I mean to say nothing more to tell. And from here we get the SI unit of Newton, which is the force required to get given mass, and this is 1 Newton, that is the force required given. This is 1 Newton to move 1 kg of an acceleration of 1 meter second square. Right. So what we get from here, we now move on to the second part, where we take about from Newton's law of motion, we move into what is called the gravitation. Right. So we again stick to the laws of Newton, that every particle attracts the other particle in a force that is proportional to the product of the mass. We all know every point mass attracts every other point of mass by a force acting along the line intersecting 2 points, and we know that can be expressed in this kind of a formula. So we know all what it is. This G is basically the Newton's constants, the gravitation constant, which is written over there, and it also can be written as this, because right, so here what happens is this is the scalar form, and yeah, so this r hat is basically a unit vector in the radial distance. Remember, it's a radial distance, it's pointing out from the center of the gravity, right, from m1 to m2, and the minus sign actually indicates that gravity is a force of attraction, not repulsion. Although law refers to point masses, it can be shown that spherically symmetric objects behave gravitationally as if all their mass is concentrated on a central point. We're not going to look much into that. Rather, from gravitation, we now move into what is called gravitational acceleration. Right, so we move ahead with the second law, the magnitude and direction, which is given. So If an object is freely falling in a gravitational field, Newton's second law tells us that the object's mass must be to be a subject of force, and this is for F equals to ma. Now the magnitude and direction of the force of a freely falling object is also given by Newton's law of gravitation, right, which is this one. And we know that experiment shows that the inertial mass capital M equals to the gravitational mass small m. So from here what we can do is that we can write this part of the equation, and then we finally write, okay, yeah, so the acceleration of a body due to gravity does not depend upon its mass, the famous feather and iron experiment. So from here we write this, right? So this is the mass of the gravitating body, for example Earth, and the minus sign indicate the acceleration decreases as r increases. Here it is. So we have till now shown the fundamental result that the acceleration of a body due to gravity does not depend on the mass. I was just telling you that the feather falls as fast as bricks, and so on. So we know these experiments, right? So inertial mass m equals to the gravitational mass m small. So we take the gravitational mass forward, acceleration forward, and this is something which is a vector description of the gravitational acceleration, and this is something which is a scalar description, which is just a kind of a notation to make things clear. So okay, so when we are talking of gravitation and acceleration, why don't we go into something which is called a gravitational field? Now gravitational field as itself, it is basically a concept. So it is a model or a concept, you can say. It is used to explain the influences that a massive body extends onto the space around itself, producing a force on another massive body. So this is a gravitational field, basically kind of a concept or a model that we physicists use in order to describe things. So the gravitational field, which we can call as G of R at any point small r, is a space defined by the gravitational force felt by a unit mass at a place at a point r. So this is a kind of a gravitating body. For example, you can consider this to be Earth. I've just given it m. So, and what we can do is that this is a, remember, it is a vector field, right? Because the gravitational force is moving the unit mass in a radial direction. So this is the radial direction, and it is found by taking the vector equation of Newton's law of gravitation, which is this one. And now what we can do, F equals to minus G, same. What we can now do is that we can just substitute one, okay, just a unit mass for one of the two masses, by putting unit mass, and what we get is this, right? So here also capital M is the mass of the gravitating body, for example Earth. So what happens is that this is the mass of the gravitating body, right? And we can plot to show the gravitational field under a uniform, this kind of a uniform sphere. Now we know about divergence, right? I'm not going back. So I have got a complete video on divergence in the playlist of Maxwell's equations. So we know, I mean to say, I'm not going to explain those partials, right? So we met the idea of divergence. We know this, it's a vector field. So it can be shown that the divergence of the gravitational field at any point is this one, nabla dot G equals to minus 4 pi G rho, right? Where this rho actually denotes the mass density. This is a Greek letter. There's the mass density at that particular point. And evidently what happens is that if the mass density, for example, we are in a space where there is no mass density is 0, so rho becomes 0 and the divergence also becomes 0, right? So this is to show you the basic concept of gravitational field. Why we are going one by one to steps, because this would be required in further approaches in general relativity, which we will look. Now this nabla dot G minus 4 pi G rho is something which our old prince of mathematics has done, which is called Gauss's law for gravity. Now Gauss's law of gravity is actually also known as Gauss's flux theorem of gravity, and it is a law of physics that is almost equivalent to Newton's law of gravitation. So it is, it says it is named after Carl Friedrich Gauss, It states that the flux or the surface integral of the gravitational field over any surface is equal to the mass enclosed. So Gauss's law for gravity is more convenient sometimes to work in than Newton. So this is what the law is. Just a quick note that the form of Gauss's law for gravity is similar to that of Gauss's law of electrostatics in the Maxwell's equations. So Gauss's law of gravity has the same mathematical relation to Newton that Gauss's law for electrostatics bears with the Coulomb's law. So I mean to say, just I wanted to make things clear. So we take a quick note on understanding these component by component. So this one is the any closed surface. This is the differential area. This G is the gravitational field. This 4 pi is the area of sphere. Now we are not going to take a derivation why it is 4 pi, because it's 4 pi r square. Some of this got cancelled. 4 pi. G is the gravitational constant and m is the total mass. So we come to this one same. So this is the divergence. This is the gravitational constant and this is the mass density at each point. So Gauss's law for gravity actually states in a closed mass in a surface integral over a closed surface. So it is good point to quickly recollect Gauss's law of gravity also. I'm going to say this is equally important, right? So this is the differential form of Gauss's law. The left hand side is the integral form of Gauss's law. Now taking from here ahead, what we need to also understand, that is the core of the today's video, that is gravitational potential and how it is related to Christoffel symbols. So named after Elwin Bruno Christoffel. So we will now look a little bit deep into what is the gravitational potential. Now the gravitational potential, as we know, is denoted by this Greek letter phi, right? This is the gravitational potential. So it is actually defined as the work done in bringing a unit mass to that point, that particular point, right, from an infinite place, infinity. So what we can say in other words, that phi is the gravitational potential energy of unit mass. Now when we talk of gravitational potential energy, the equation that immediately comes in our mind is this one, right? So potential energy is this. We already know that from our school day physics. Again, letting one of the masses equal to 1 kilogram, for example, we put this, we can define the gravitational potential field, which is a scalar field, as this one, right? Phi equals to, this should be not minus, I'm sorry, it should be minus gm by r. And if we take a kind of a point at a distance r from the point mass, yeah, so for a point at a distance r from the point, from the center and outside the uniform sphere of mass m. So if the sphere has the radius capital R, right, this one would be true, right? This one would be true. So for instance, inside a uniform spherical mass, if I take this one, right, the inside, you can see this one, right, this one. So for inside a uniform spherical mass, that is for small r, this one, if I take the small, this holds for r which is greater than r, but in case that we take in uniform mass where small r is less than big R, right? So this is actually what happens. A little bit, in comes up the derivation. So phi equals to minus gm2 r cube. Thanks that I have written this time correct. So right, and now what we can do is that, yeah. So this is r3 r square minus r square. Yeah. So this holds actually when small r is less than big R. And this holds phi equals to, it should be minus gm by r. Anyway, so if r is greater than equals to r, right? So at a point m at a distance r from the center and outside a uniform sphere of mass, this happens, and inside for a point uniform mass where it is inside, this happens, right? Okay, so we now take a step back and we want to go back to that cuboid concept. Now why? Because we want to understand something which is called the magnitude of a position vector. So if we take these lines, right, and what we get from here is that position vector or radial vector r from the origin O. So we get this one, right? We already know this. So we know that r equals to this one, x square root of the radical of x square plus y square. So in Cartesian coordinates we can now rewrite the gravitational potential, which was this one, phi equals to minus gm by r. Thankfully I have corrected this here, right? So equals to minus gm. So this is the Cartesian coordinate. I just wanted to take this example of cuboid so that we understand that how the square root of the denominator comes. Now also note that we use this nabla operator, this differential operator, and this is basically used for three reasons. It calculates the divergence, gradient, and curl. Now if we use this nabla, which is of a scalar field phi, then what we get is this one, right? So what we get is this one. I think this part is quite clear. So we take this value, okay, this one, yeah, this is the gradient obviously. So what we do is that in ordinary Euclidean space, for a point a scalar phi, the gradient is the vector points. So we take this one, this is the partial differentials, and then we get this one, right? Then we use the differential operator and we get this value. Calculating further, we get this value. Now I'm not explaining it right now because this requires a kind of a differential operator calculator, which you can just check on the equations. So we further go and we get this, and now what we do is that we get, ultimately the answer is this. Now as because this small r equals to the modulus of this, what we can do is that we can write, yeah, this one, I mean to say this equal as this, right? And now by definition, r equals to xyz equals to this is by definition, yeah, given r. So it denotes an ordinary Cartesian vector, right? So the basis vectors are implied, and we know that we don't bother to show them. So now we can rewrite this one, it gets cancelled off, this one r cube and all this get cancelled off, and we finally arrive into this. And this is how it is treated, right? So now what we do is that we find this one. So this part is actually this part, right? So this is, okay, let me explain to you again. So now we have found an equation that relates the gravitational potential field with that of the gravitational field, because this, the right hand side of it is equals to this, which we have dealt earlier. So this is the phi, the gravitational potential field, which is a scalar field, and this is the gravitational field, which is a vector field, and somehow there's a relation between these two fields. And finally what we do is that it's a gravitational field. So if G we replace it by nabla phi, and we get this, right? So you can check onto this part. I mean to say this is pretty simple. I just trying to get in a kind of a relation between the gravitational potential field, which is a scalar, with a vector, and we use those differential operators in order to get this. So till now what we have learned is that the gravitational potential, and also we looked into how the gravitational potential field can be used in order to make a construct of a sphere where the solid sphere is inside and outside. So I hope but this is okay. Now the problem is that when we are dealing with general theory of relativity, gravitational potential, etc., the geometry changes with curved spacetime. And with curved spacetime, we need a different tool in order to establish a kind of a connection. So that is what the Christoffel symbols does. So in general, again, you will get a wrong notion that Christoffel symbols denotes gravity or gravitational potential. It does in a different way. So Christoffel symbols represent the connection coefficients of the Levi-Civita connection. Don't worry, I'm coming to that. And they describe a change in the basis vectors through a given coordinate. And it represents the fictitious forces induced by a non-inertial frame of reference, non-inertial frame which is moving. So what we are trying to make a point over here is that when the basis of the vectors, we will soon see examples, changes, then we need a kind of a connection. and the Christoffel symbols actually does that. But before that, we'll very quickly take a look in what is called an affine connection. So the notion of affine connection has its root in the 19th century geometry, I mean to say tensor calculus. It was developed later in the 1920s by Eli Cartan, right, and Hermann Weyl. So the many invariants of an affine connection are its torsion and curvature. This is a illustration of torsion. So you can see these are the tangent vector fields which connects, and it can be differentiated. Okay, so I will go step by step. What I'm trying to make a point is that, see, in Riemannian or any pseudo-Riemannian geometry, we deal with manifolds, right? This manifold, each of these manifolds are characterized by what is called an affine connection. They do have an affine connection, right? Now, the manifolds also is characterized by what is called a metric tensor, which measures the causal structure of space-time and many other things. We know what is a metric tensor. Now, these type of manifolds who have a metric tensor, they are actually called Riemannian manifolds, right? Those who have a metric tensor. Now, these Riemannian manifolds also have what is called an affine connection, and these affine connections are called Levi-Civita connection, right? It's named by Tullio Levi. I don't remember the name of Civita right now, but Tullio Levi-Civita connection. So the Levi-Civita connection, I can tell it is a very special case of an affine connection, obviously. It is the affine connection for a manifold with a metric, right? So it is basically an affine connection of a manifold with a metric. Now, what happens typically is that we need this affine connection, or I would say the affine connection is already there because it connects the nearby tangent faces so that we can differentiate and do a better connection. And Levi-Civita connection is basically a special affine connection which we will see soon how it behaves. Okay, so now we take a quick look, but I was telling that we need a special tool. What is that? That is called a connection. Now, what happens is that in the case of transporting local geometric objects from a place to others, etc., tangent vectors and tensor, so we need a long family of curves in a parallel and consistent manner. So a choice of an affine connection is also equivalent to the notion of what is called a parallel transport, which is a method of transporting tangent vectors along curves. Now, I will just use the analogy which I have used earlier in my videos also, that how will you understand which one is bigger? I mean to say, simple concept of congruency. So we put one another arrow on the other, and if it overlaps, then it is bigger. This is obviously the smaller one, right? Now, what we do, it is a way of comparing vectors at different positions of manifold. I mean to say, the connection actually does what the parallel transport helps. It's a way of transporting data along smooth surfaces. So let me quickly, explain with that. So here is a triangle, and I've got a point, this one red. I'm trying to move and trying to keep it as safe as possible. I do that, and then this, you see that red arrow pointing towards right overlaps that. That means in flat space, when we have parallel transport of a vector, it comes back to the original point. So we have no problem with that. But general relativity has got complexities and it has got curvature. So we take this kind of a sphere and we stand over here. This is the red point, and we are trying to go to the blue point. And we are carrying a kind of a spare or a arrow which we will try to keep as straight as possible. The original arrow is marked in yellow. So I move over from here. It is called V, and I'm trying to keep it, but you still see that the arrows are bending, and this is because due to the curvature. Now from this point we try to go from the equator. We are trying to keep it as clear as possible. So here, the direction of the vector is due to the curvature. And then from here we try to move back to our original place, right? So we are keeping this as straight as possible here also. But this one, when we come back, is a V prime, which is totally different in the direction where we started. That's the yellow vector. So when we take out this yellow vector and this, we find there's a difference, V and V prime. So parallel transport, which is trying to move around the sphere it tries to make the sphere as constant as possible, but it is not. So parallel transport cannot keep vectors and all that. We need something which is called a covariant derivative. Don't worry about the term, I will soon explain you. And covariant derivative is a tool which helps us to find parallel transported vector fields. Now who will find the parallel transported vector fields? The covariant derivative, and in connection with another value. Okay. So connections are basically local geometric objects. They allow a comparison between local geometry at one point and local geometry at another. This has got two types of connection, one which measures infinite symbols and another which measures local theory. And these are the different type of connections. However, we are just dealing with the Levi-Civita connection. So just to tell you that what actually the connections are. Okay, so we know this is a kind of a covariant derivative, and this is being replaced by the nabla operator, which is a covariant derivative. Actually, what happens is that Levi-Civita connection refers to the covariant derivative. What do we mean by covariant derivative? I'm not clearly telling you, but it's a kind of a derivative, right? So, in a nice intuitive way to think about these connection coefficients is to think them that they are corrections of an ordinary derivative, right? So, because the ordinary derivatives cannot work here, because the basis of the vector changes, how it changes I will demonstrate to you soon. Hence, Levi-Civita connection comes to save this and do the necessary corrections to an ordinary derivative. So let me explain you the components of this Levi-Civita connection. So first we go with this, right? This one is basically the Levi-Civita connection which connects nearby tangent spaces, defining a corrected notion of the derivative in arbitrary coordinates or arbitrary manifolds. That means there is something wrong. That means ordinary derivatives are not being happening. We are using covariant derivative, and in order to do that there is a tool which is the connection. This is the Levi-Civita connection, right? So we looked at the second component, which is pretty easy. This is basically the ordinary derivative, which basically is defined of a tangent space, for example in Cartesian coordinates. And this is actually, this gamma term is actually a correction term. Remember, it is a correction term called the connection coefficient or Christoffel symbol, and this is corrects the ordinary derivative for an arbitrary or manifold or a coordinate system. So here note that the indices really doesn't make any sense. This was because the covariant derivative is an operator that needs to act on something, so the indices really doesn't make any sense. So all in all, this is a connection. You understood what is a connection. Either it is distinct with local theory or infinitesimal. It is a kind of a connection which helps us to correct the ordinary derivative which is not possible on a curved manifold. Okay, so these are all mathematical calculations, but as always I prefer in the video to show a geometric meaning of Christoffel symbols so that it becomes clear how it looks like. So geometrically, Christoffel symbols can be interpreted as describing how basis vectors changes through a coordinate system, right? So the basis vectors may change even due to the coordinate system being curvilinear or due to the geometry of the space as it is being curved. So here I have written the Christoffel symbols essentially defined as the derivatives of basis vectors. Okay. So here is the kind of a vector, and what I'm going to do is that I'm going to explain it. So this is how much the basis vector E mu changes when it moves along the x nu axis. So you can coordinate. This is actually what is called the dot product. Now I have got a separate video which deals with the deep details of what is a dot product and cross product. So intuitively understand this dot product describes how much this derivative and the basis actually overlaps. So it overlaps and it is absolutely overlap. That means that they are the same and so on. Okay, so I would like to explain you geometrically what is the basis vector, its changes, and what all those problems are all about. So in a flat space we get a vector called A, and this is being measured by the component AY and AX. And if I draw the lines, it are more or less the same. Now if I take a kind of a curved surface and I plot the same, I get a curved surface. Let's look, yeah, something like this. So x, y goes into x prime and y prime. And I'm trying to make this vector the same, but I'm trying to make the measure of this vector through those components. So you see the x component is something here and the y component goes something here. So what happens is that when I join those, I see a prime x is longer than ax. We see that a prime y is also longer than ay, but the a remains invariant, right? So a remains invariant in the sense that it doesn't change. So this is the problem, that the basis of the vectors are changing in curved space. So now let us say that we have some curved coordinate system. This is one, x1, this could be t or x2, anything that you like, and this is the basis vectors, like, okay, so these are just labeled as e1, et and ex. So what happens is that if you really calculate the dot product, which we used to do in uv in the typical Cartesian coordinates, the basis vector changes in the time direction, and we cannot do this u dot v equal to the components. We cannot do, because you see here in curved space-time things are changing. So we take this one and we plot this one as x1 and x2. This is a curved space, right? Curved coordinate system with x1, x2, with the basis vectors which are these, which are e1 and e2. Now just try to imagine, this is very important. Imagine that you move along the x1 axis and see how the basis of vector e2 changes along the x1 axis, right? So a small change in a vector along a coordinate axis is simply the partial derivative with respect to the particular coordinate. Obviously, you have to do a partial derivative because it's changing on a curved manifold. So this derivative vector, this one, we take the red one, can also can also components along the x1 and x2 axis, obviously. So this is done by taking the dot product of the red vector, which I will show you. This is a derivative vector, right? And the Christoffel symbols are basically telling how the basis vectors are changing, how they're actually changing. Okay, so we see this one, which if I differentiate, takes this for equation, this one and this one. So all in all, if you don't want to go into the mathematical details of calculating those derivatives, then understand that Christoffel symbols geometrically represent different components of the derivative of basic vectors. Remember, this is the different components of the derivative of basic vectors, because the basis vector changes with the curved space-time. So if you were to take the derivative of basis vector, this would give another vector, right? So the Christoffel symbols then represent the different components of this new vector. All these things changes. Now from this Christoffel symbol, how the basis vectors changes and all those, you will see that there is an underlying force which is also working. So these are in bold. Remember, these are corrections to an ordinary derivative. Okay. Now if these Christoffel symbols, which are corrections in terms of derivative, if they are written in the metric form, then how it would be? Let us have a quick look on that. So we know that G mu nu is the metric tensor to define the geometric concept on arbitrary coordinate system. So we get a kind of a, I would say, equation like this. We get a kind of a equation like this, and don't worry, I will just explain to you. So you see these derivatives, these are partial derivatives of the metric with respect to the different space-time coordinates. This is basically the metric. When I'm writing the Levi-Civita in terms of this metric, this is actually happens, right? And this one is the index, is a summation. It is a summation from 0 to 3 for dimension, please. So what I'm trying to make a point over here is that the metric tensor, to put simply, is used to define different geometric concepts in arbitrary coordinate system. The metric is, as you know, is denoted by G mu nu. So the Christoffels, now the Christoffel symbols in the term of metric, it is thus how it is explained. Okay, so what we draw a conclusion from here is that gravity is obviously a fictitious force in general relativity. Christoffel symbols, because they are denoting a change in basic vectors. Anything that changes, it moves. So the change of basic vectors obviously will give rise to fictitious force. If you have gone to my earlier videos on geodesics and Ricci scalar, you will find that how the basis of vectors changes and the geodesics are causing a curvature which is called gravity in relativity, right? So the change in basic vector usually gives rise to a fictitious force. The Christoffel symbols actually describe what are those fictitious forces, and it plays the role of describing how objects actually move or get accelerated, because it is actually showing the change, right? And Christoffel symbols are gravitational fields in general relativity because it is subject to change. So the gravitational potential of Isaac Newton is being replaced by this one, that is G mu nu, the metric tensor, and the gravitational force field is being replaced by this Christoffel symbol. Now, in order to understand what it is, I will like to give you a quick and a very simple comparison without examples, as you understand physics is not complete. So in Newtonian gravity, the gravitational field, that is the gravitational acceleration at each point in the field, is represented as a vector field, right? So this G, which you can see, is defined as the negative gradient of the gravitational potential. That is why it's a minus sign. So all these are partial derivatives of the gravitational potential. Remember that these are all partial derivatives of the gravitational potential. Now if I write this one, right, you will see these are the partial derivatives of the metric. It's a big difference, right? So the Newtonian gravitational potential partial derivatives are the gravitational potential, while in general relativity partial derivatives are that of the metric, and that is why gravitational potential is replaced by the metric tensor. So I hope, yeah, you can understand what I'm trying to make. Trying to make a point that how this shift really happens, and this the partial derivatives in both the cases, these are partial derivatives. In this case, Newtonian case, it's gravitational potential, and this is the metric. Okay, now there is something which is called a weak field approximation. It is just a hypothetical case when gravity is less and the complications are less and things are moving slow. You will see that Christoffel symbols are reduced, which looks almost like Newtonian gravitational field. So this is the geodesic equation of weak field in general relativity, and you see this one. This is the equation of motion in Newtonian gravity. Doesn't it look the same in weak field limit? And this is the Christoffel symbol which looks at this limit. So finally we come that Christoffel symbols represent gravitational acceleration in general relativity. Why? Because it denotes the change of the basis of vectors, and with that change it causes the gravitational acceleration. Okay, so just finally I just wanted to show you that the geodesic equation is basically the second law of Newton, and the Einstein field equation is basically the Poisson's equation, right? So now when we are talking of Poisson's equation, we need to look how Poisson's equation actually reflects Einstein's field equation, and that is basically what is coming up in the next part of our video. We are going to look into Poisson's equation, Minkowski metric, pseudo-Riemannian manifold, geodesics, parallel transport, Riemann curvature tensor, Ricci tensor, Ricci scalar, space-time, geodesics, energy momentum tensor, and finally the Schwarzschild metric. So yeah, the mathematics of general relativity will be intense, it will be long, so I thought to divide it into different parts. So I haven't gone into the real summing up or the summary of this video, because it is all mathematical, and these concepts really require a summary which you can use it too. So this is all I mean to say. We started with Euclid, then we moved into gravitational potential, and then from gravitational potential we showed that how this is related to Christoffel symbols. Further in from Christoffel symbols, how the connection actually helps, what are the different connections, and so on. So I will put a pause and I will write to thank you for watching this video. What you can do is that you can put up your comment, and I'm sorry for the minor mistakes in signatures, signs, etc. And that's it. Please do subscribe to my channel Physics for Students. Do like, do comment as you do, because these are motivational facts. These are motivations which keeps me moving and helps me to improve on my video. Do also click on the bell notification, click on all to get all the notification from Physics for Students. Thank you very much. This is Shaunak signing off from Physics for Students, promising to come back very soon with another interesting video. Till then, enjoy the winter, season's greetings, and best wishes. Goodbye until next time.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.